So last unit, we really introduced some new quantitative aspects of chemistry. We talked about moles and the mole to gram conversion and the mole to atom or molecule or formula unit conversion by using Avogadro's number. So we did a lot of new math. However, the only value in what we did was if we are dealing with one molecule. And so what we're going to do in this unit is we're going to combine together the first unit we started with this semester, chemical reactions, with the quantitative aspects of what we learned. Because if I start with a certain amount of reactant, I would like to be able to determine how much product should be formed. And at the moment, I can't do that. So let me show you a couple of real-world examples to make this make sense. All right, so the equivalent of what we're doing, which is stoichiometry, we're going to do stoichiometry today, is the equivalent of a recipe. So if you notice in this recipe, it takes 1 cup of flour, 2 eggs, a half teaspoon of baking powder to make 5 pancakes. So if I ask you, hey, I have 12 eggs, how many pancakes can I make with that? Then what I can do is the proper conversion setup that we've been doing so far. So if I tell you I have 12 eggs, what I can do is get out of eggs, put eggs on bottom, and then I can get into what I want to get into, which is pancakes on top. And what I'm going to do is I'm going to use these values, these coefficients, I'm going to throw a chemistry term in there, in order to note the relationship. So 5 pancakes are going to be made when I have 2 eggs. And so the answer I get here is going to be 30 pancakes. I can make 30 pancakes if I have 12 eggs. Okay? So that concept of taking a given for a reactant and using these coefficients to be able to figure out how much product is going to form is what we're going to be doing in this section. Now, what if instead I said, hey, I want to make 25 pancakes. That's my given. How many teaspoons of baking powder do I need? So I'm actually going backwards. I'm starting with my product, and I'm going to go backwards in order to determine the amount of baking powder I need. So I'm solving for the number of teaspoons. Okay, so if you look at our recipe, I know that 5 pancakes require a half teaspoon of baking powder. Okay, so what that'll give me, 25 times a half divided by 5 will give me 2.5 teaspoons. So stoichiometry enables me to convert between the amount of reactants I have to the amount of products, or from the amount of products I have to the amount of reactants. Or I could even say, hey, if I want to make enough pancakes to use up 2 cups of flour, how many eggs would I need? And you could also use that conversion by simply using these lovely coefficients. Now, the important thing here is that the coefficients enable us to convert between different ingredients or different products. So that should impress on you the importance of making sure your reaction is balanced. All right, so let's look at our first example here in chemistry terms. So it gives me this formula: aluminum reacts with oxygen to form aluminum oxide. So the first thing I need to do before I do anything, I need to balance. Okay, so I've got 2 oxygens here, 3 oxygens here, so I know that I'm going to need to make that equal to 6. So I'm going to put a 3 in front of oxygen and a 2 in front of aluminum oxide. That does mess up my number of aluminums. I now have 4 aluminums on my product side, so I'm going to put a 4 right there. Okay. Now I have a balanced reaction, and so I can do a conversion. For A, it says how many moles of aluminum are needed to form 3.7 moles of aluminum oxide. So my given here is 3.7 moles of aluminum oxide, and I want to get into moles of just aluminum. So I'm going to put moles of aluminum oxide on bottom, and I'm going to get into moles of aluminum on top. Okay? And so the only thing I need to do now is look at my coefficients, just like I did in the recipe example, in order to do that conversion. Well, the coefficient in front of aluminum is 4. The coefficient in front of aluminum is 2. So I'm going to take 3.7 multiplied by 4 divided by 2, and the answer that I get is 7.4 moles of aluminum. Okay? I'm going to make a couple of quick notes here. First of all, this relationship right here, this is called my mole-to-mole ratio, and you get it by using the coefficients of a balanced reaction. Second point, notice how detailed I am with my units. Moles of aluminum oxide, moles of aluminum oxide, moles of aluminum. I need you to be that detailed when you're working on your own problem. And then finally, notice that I have 2 sig figs in what I'm given, and I gave you 2 sig figs for your final answer. I'm not going to be using these coefficients for sig figs because those are exact values. I am counting the number of moles. Okay? Let's try one more mole-to-mole conversion. So how many moles of oxygen are required to completely react with 14.8 moles of aluminum? So if I'm giving you moles of aluminum, I'm asking you, hey, how many moles of oxygen are going to be required to react with that? So I'm going to get into moles of oxygen, moles of O2. I'm going to use my mole-to-mole ratio. Well, the coefficient in front of oxygen is a 3. The coefficient in front of aluminum is a 4. So I'm going to take 14.8 and I'm going to divide by 4 and multiply by 3, and I get 11.1 moles of oxygen. Notice the amount of detail I'm giving. Notice that my given has 3 sig figs, 1, 2, 3, and my final answer has 1, 2, 3 sig figs as well. Okay? Well, that's great, but what if instead of asking you to convert from moles to moles, what if I gave you, let's say for example, grams of one reactant and asked you to figure out the grams of product that it would form? Notice this wheel should look familiar. We used it in the last unit. So if I give you grams of a substance, let's say substance A, and I want to get into grams of substance B, what you would do is you'd first go from grams of substance A to moles of substance A. Once I have my moles of substance A, I can get into moles of substance B by using my mole-to-mole ratio, and then I can get into grams of substance B. Okay? The other really cool thing you should know, what if instead of asking for the grams of substance B, I asked for the, let's say for example, the atoms of substance B? Well, if I went from grams of A to moles of A, from moles of A to moles of B, then I could go from moles of B into atoms of B. Okay? So let's look at some examples to really make sure this makes sense. All right, for the first problem, calculate the number of grams of NH3 produced by the reaction of 5.40 grams of hydrogen with excess nitrogen. This is my equation. Notice it's not yet balanced, so I first have to balance it. Well, I've got 2 nitrogens, so I'm going to put a 2 in front of ammonia. Now I have 6 hydrogens from my product side, so I'm going to put a 3 in front of hydrogen. All right, now I can start. So I'm going to start with my given, which is 5.40 grams. Okay? And I'm going to quickly track out what I'm going to do in the diagram above for you. So I need to go from grams of hydrogen into grams of NH3. So I'm going to go from grams of hydrogen into moles of hydrogen, from moles of hydrogen into moles of NH3, then from moles of NH3 into grams of NH3. Okay, so let's actually do that. So I have 5.40 grams of hydrogen. I'm going to put grams of hydrogen on bottom, and I'm going to put moles of hydrogen up top. I'm not going to plug in anything yet. I'm going to just keep going. I don't want to stay in moles of hydrogen because I'm concerned about NH3. So I'm going to put moles of hydrogen on bottom, and I'm going to put moles of NH3 up top now. Okay? Now, I don't want to stay in moles of NH3 because I want to know my grams of NH3. Okay, so I'm going to put grams of NH3 up top. So notice the only really new thing here is the fact that I can use a mole-to-mole ratio. This gram-to-mole conversion and mole-to-gram conversion is not new. Okay, now I need, for grams to moles for hydrogen, I need my molar mass of hydrogen. Well, hydrogen is 1.008, but I have 2 of them. So the molar mass of H2 is going to be 2.016 grams for every 1 mole of hydrogen. For the mole-to-mole ratio between NH3 and H2, I have 2 moles of NH3 for every 3 moles of hydrogen because I'm using my coefficients. Then to get into grams of NH3, I need to determine the molar mass of NH3. So the molar mass of nitrogen is 14.007. I'm going to add to that the molar mass of hydrogen, which is 1.008, and multiply that by 3. And so the molar mass of NH3 that I get is 17.031 grams for every 1 mole. Okay, so now what I'm going to do in my calculator, 5.4, I'm going to divide that by 2.016. Then I'm going to multiply that by 2, divide it by 3, and then multiply by 17.031. And the answer that I get unrounded is 30.4125. My units are grams of ammonia. Okay, now let's figure out sig figs. I've got 1, 2, 3 sig figs from H2. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so obviously 3 is my fewest number of sig figs. So I'm now going to round this to 1, 2, 3 sig figs. So this is going to be 30.4 grams of ammonia. Okay, so I'm now able to convert between grams of one substance into grams of a new substance. Well, what if I'm not asking about grams to grams? What if I want to go from grams of one substance into molecules of another substance? Can I do that? And the answer is absolutely. So let's look at this example here. Okay, how many molecules of oxygen form when 3.61 grams of potassium chlorate react in the reaction? Okay, so I need to make sure to balance this first. So notice I've got 3 oxygens, 2 oxygens, so I'm going to put a 3 in front of oxygen here and a 2 in front of potassium chlorate. That'll make 2 potassiums, so if I put a 2 in front of potassium chloride, I will now be balanced. Okay, let's now put my given. So 0.361, my units are grams of potassium chlorate. Okay, so let's go back to this table or this diagram and see where I'm going to go. I'm going to go from grams into moles of potassium chlorate, just like I did before. Then moles of potassium chlorate into moles of oxygen. But now instead of going into grams of oxygen, I'm now going to get into molecules of oxygen by using Avogadro's number. Okay, so let's do it. So I'm going to put grams of potassium chlorate on bottom, and I'm going to get into moles of potassium chlorate up top. I don't want to stay in moles of potassium chlorate though, so I'm going to do another conversion. I'm going to put moles of potassium chlorate on bottom, and I'm going to get into moles of oxygen first. Now that I'm in moles of oxygen, I can easily get into molecules of oxygen. And so I'm going to do that in my last step. Okay, let's plug in all of my values. So I first have to determine the molar mass of potassium chlorate. Potassium has a molar mass of 39.098. Okay, chlorine is 35.453, and then oxygen is 15.999, but I need to multiply that by 3. And so the molar mass I get for potassium chlorate is 122.548 grams for every 1 mole. Here, my mole-to-mole ratio, I need to use my coefficient. So my coefficient for oxygen is a 3. My coefficient for potassium chlorate is a 2. And then for my molecule and mole conversion, I'm going to use Avogadro's number, 6.02 times 10 to the 23rd. And my unit and my value for moles will be 1. Okay. So I'm going to take 0.361, divide it by the molar mass of potassium chlorate, multiply by 3, divide it by 2, and then multiply by 6.02 times 10 to the 23rd. And the value that I get here, unrounded, is 2.6600 times 10 to the 21st. Okay. Keep in mind, I want 1, 2, 3 significant figures. This has 6, which is way too many. Sig 0.02 has 3, so I'm going to round this to 3 sig figs. 1, 2, 3. So I have 2.66 times 10 to the 21st. And my units here are going to be molecules. And I am done. So really the only new thing in this lesson was my mole to mole conversion, because otherwise the other conversions we have already done.